Alright, hello everybody, and welcome back to the physics videos. Today we are going to start a new topic, and it's something called uniform circular motion. So before we get started, I want to throw up the homework questions so you can be looking for how to answer these problems as we go through the lecture. So the first question asks you to draw the path of the moon orbiting the Earth from the perspective of an alien not on Earth. So you're looking at the Earth and the moon. Your drawing must include the direction of travel of the moon, or its velocity, the direction of acceleration of the moon, and any forces acting on the moon. So I want a nice diagram with lots of arrows. Different colored arrows for different things would be awesome. Not required, as long as you label clearly. 2, the orbital speed of the Earth is about 30 kilometers per second. Assuming the Earth's orbit is a circle with a radius of 150 times 10 to the 6 kilometers, what is the Earth's centripetal acceleration? So, up to now, we have been focusing on objects that are basically moving in a straight path. When we talk about acceleration, we're really talking about it as a change in speed per unit time. We've really only been talking about acceleration as slowing down or speeding up of an object. But now we need to look at it from a different perspective and ask the question, what happens to an object's motion if we keep the speed constant and just change its direction? And this question brings us to the topic of uniform circular motion. And we define uniform circular motion as motion in a circle of constant radius at a constant speed. So what that means, for example, if we look at the picture of a ball on a string being twirled around, that means the radius does not change. The ball will not get closer or farther away from the center point. It will always stay the same. This right here is constant. And it also means that as the ball is being spun around, it will not speed up or slow down. Its speed stays the same. So the length of that arrow, its speed, the magnitude of velocity, will stay the same. So when we actually talk about the velocity of an object in uniform circular motion, we talk about its instantaneous or tangential velocity. And tangential is one of those weird geometry words. What that means is when we look at the velocity of an object, if this ball is traveling around the circle this way, its velocity at this exact point is equal to starting at the center of the object and moving straight out from the circle. So for example, if I were spinning a ball around like this and all of a sudden the string broke, the ball would continue moving along this yellow arrow because that is the direction of its velocity at that exact point. However, if we look up at the ball up here, it's the same ball traveling around in a circle, but its tangential velocity right now starts at the center and moves straight out from the circle. So the size of these arrows is going to be the same. The speed the ball travels is always the same, but the direction is constantly changing. So velocity is always tangent to the circle, and the speed stays the same. And we can look at that using this little applet. So the first circle, the big one with the arrow and the red dot right now, just shows the radius. The arrow will follow a point on this circle. So let's assume that that red point is a ball on a string being spun around. I can also show the velocity of this object as it moves around, and that is the second circle with the blue arrow. And remember, the velocity of the object is always tangent to the circle. So you would start at your object and draw straight out from the circle. And I can also show acceleration, but we'll get to that in a second. So if I start this ball moving around, you can see as the red dot goes around, the velocity arrow is always changing. The size of it never changes because this ball is moving at a constant speed, but its direction always changes. And its direction of velocity is always going to be at a 90-degree angle to that white arrow. And that's what tangential means. It's coming straight off the object out away from the circle, and it will make a 90-degree angle with any line you draw from your object to the center of your circle. If we look at acceleration, it gets a little funky. It turns out the acceleration of this object, which it won't let me choose, turns out the acceleration of this object always, always, always points toward the center of the circle, which is kind of weird to think about, but it's true. If you have a ball on a string and you're whirling it around, the only thing keeping it in that circle instead of flying off to the side is the acceleration, which is pulling it back in toward the center of the circle. There we go. So the velocity of an object moving in uniform circular motion is always tangential. It will always make a right angle with any line you draw toward the center of the circle. In order to really understand uniform circular motion, we have to know something about an object traveling in a circle. So let's define a few important things. The first definition is the period, and this is measured in seconds. The period is the amount of time required for one revolution of an object. So if I have a circle, and I want to know what the period is, let's say I have a ball moving around the circle. The time it takes for the ball to start here, go all the way around, and come back to the same spot is the period. And the symbol for period is a capital T. I know it doesn't make a whole lot of sense, but that is just the way it is. So the time for one complete loop of that circle is the period, and it's measured in seconds. The frequency is related to the period, but it's a little harder to wrap your head around, at least for most people. The frequency of an object is the number of revolutions you can do in a single second. So, for example, if we go back to our circle over here, if I can start right here and go around the circle twice in 1 second, that means I have a frequency of 2. I can do 2 cycles in 1 second. So, number of times around in a second is our frequency. And that symbol makes much more sense. It's a little f. Now, we are measuring the number of times around in a second, which is a weird unit. It turns out the unit for frequency is an inverse second. It's 1 over a second, and we call that a hertz. So the frequency of an object is measured in hertz, Hz. And it turns out that period and frequency are related. They are the inverse of one another. So, if it takes half a second to go around, that is our period. Our period is half a second. That also means that in 1 second, we can do 2 revolutions. That is our frequency. Our frequency is 2. And 2 is the inverse of 1/2. If you do 1 over 2, you get a half. If you do 1 over a half, you get 2. So that is how frequency and period are related. They both describe to us how fast an object is going. And you should know this one from math class, but just in case you've forgotten, the circumference of a circle is the distance around the edge of the circle. So if we start at our object here, and it moves all the way around along our circle and comes back, the distance that object traveled is the circumference. And we measure circumference by the equation 2 pi r. Hopefully you all remember that, but just a refresher. So, basic terms for motion in a circle: period, amount of time to go around once; frequency, number of times to go around in 1 single second; and circumference, the distance traveled by the object. So we already know that the speed of an object in uniform circular motion does not change, but its velocity does. How does that make sense? Well, speed and velocity are very, very similar, but remember, speed is a scalar quantity and velocity is a vector quantity. And vectors always have direction, and the direction in uniform circular motion is always changing. And we can see that by looking at these two green velocity vectors on our picture. The length of these arrows is the same, which means that the speed does not change, but the direction is different. This one is pointing over to the right. This one is pointing down and to the left a little bit. Those are totally different directions, which means they are different velocities. So the speed, or the magnitude of velocity, how long that arrow is, can be found using some of the things that we have just defined. So we know from way back in the year that velocity is distance traveled by an object divided by how long it took to do that traveling. So distance divided by time. When we talk about a circle, we know the distance traveled for one complete circle is the circumference. And if we're talking about how long it takes to travel in that one cycle, that is the period. So to find the velocity of an object moving in uniform circular motion, we take the circumference, which is the distance it travels for one circle, and divide it by the period, which is how long it takes to do that one circle. So now we know that velocity is always changing because the direction of that velocity is always changing. So, given our definition of acceleration, which is a change in velocity, this object must always be accelerating. Right? There must be an acceleration on the object to change the direction of velocity. So if we continue with this definition of acceleration as a change in velocity, we can look at what happens when the change in velocity becomes very small. So all that I'm doing is in my head, I'm imagining, okay, we have our tangential velocity of the ball at point A, and we have the tangential velocity of the ball at point B. The speeds here are the same, but velocities are different because they are pointing in different directions. And I want to imagine in my head what happens when I bring points A and B really super close together so that that change in direction gets really small. And we end up with a picture like this, where we have our initial velocity from A, which is v1 right here. Choose a different color. And we have our second velocity from point B, which is v2, and we add them together. And what we get is our result. This is the change in that velocity, how much the direction changes over that time period. And when we look at that, when we get our change in velocity, that is our acceleration, right? Acceleration is a change in velocity. And we can see that acceleration points toward the center of the circle. And that is exactly what we saw in our applet here. If I play this again, the purple arrow, or acceleration, is always pointing opposite the direction of the white arrow. And that is telling us that in order to keep that red dot moving around and around in a circle, it needs to be accelerating toward the center all the time. We call this acceleration pointing toward the center, this guy right here, centripetal acceleration. And we will write that as A with a little c underneath. And that way we know this acceleration is pointing toward the center of a circle to keep an object in uniform circular motion. It is not a linear acceleration. So centripetal is a Latin word that means center seeking. And this makes sense because the acceleration is always pointing toward the center. It is making the object seek out the center of the circle. And we have a special formula to calculate the centripetal acceleration of an object. And that is the velocity of the object squared divided by the radius of the circle. So we take how fast the object is moving, square that number, divide by how big the radius of the circle is, and that will tell us how fast it is accelerating toward the center of the circle. This is a super important equation, and I want you to write it in your notes somewhere where you will not lose it. So the acceleration always points toward the center of the circle. And for uniform circular motion, we always call toward the center positive. So anytime the object is moving around the circle, its acceleration always points toward the center. And we always call this positive. Always. So now let's try and apply some of what we've learned today to a sample problem. So we have a circle with a radius of 4 meters. So let's go ahead and label that on our drawing. The radius is 4 meters. And our object, our little green ball here, makes 4 revolutions in 2 seconds. So that means it will start here and it will go around 4 separate times, and it will do that in 2 seconds. 4 cycles in 2 seconds. What is its centripetal acceleration? Well, the first thing that we should do is write down our equation for centripetal acceleration. That way we know what we need to solve for this. So our equation for centripetal acceleration, you all wrote it down in your notes, I know, is the square of the velocity of the object divided by the radius. So we already have one of these things. We already know the radius of this circle, right? The radius is equal to 4 meters. But we do not know right now the velocity of this object. V equals question mark. However, we can do a little bit of math magic to find out how fast this object is moving. What we need to do is think about, okay, how do we calculate the velocity of an object? Well, we know that velocity is distance traveled over time, always. Whether it's in a circle or in a straight line, it's always the distance traveled over time. And hopefully this is looking familiar to you, because we did this earlier in the video. The distance traveled can be found by using some of our circle math. So the distance that the object travels when it goes all the way around the circle and comes back to the same point is the circumference, right? The object starts here, it travels all the way around and comes back, and that is the circumference. That is how far it goes. And we calculate circumference with the equation 2 pi r. Now time. Well, the time it takes to go that distance is going to be however long it takes to go all the way around the circle and come back once. So we know that this object will go around the circle 4 times in 2 seconds. So if we think about that, it goes around 1, 2, 3, 4 in 2 seconds. So one of those cycles has to be half a second. all we do is we take the number of cycles and we think about how long it took to do that. And that took 2 seconds. So then if we take 2 seconds and we divide that by 4, that means 1 revolution is going to take half a second, right? If we count, it goes half, 1, 1.5, 2. 4 circles in 2 seconds. So that means the time it takes to go around, going back to our blue velocity equation over here, is 0.5 seconds. So now what we can do is we can plug in for the radius here and solve for our velocity. So velocity is equal to 2 times pi, and the radius is 4, divided by 0.5. And when you plug that into your calculator, you do have a pi symbol. Hopefully you all know where that is. If you don't, you should ask. So it's 2 times pi times 4, and then you divide that by 0.5. And this comes out to be a velocity of 50.26 meters per second. So this thing is cruising. It is going pretty darn fast. And we just found its velocity. So now what we can do is we can use this number in our acceleration equation. So centripetal acceleration is velocity squared over the radius. We now know velocity is 50.26, and we need to square that, and then after it is squared, we can divide by the radius, which is 4 meters. So when you plug this into your calculator, 50.26, and you square it, and then you divide by 4, you get a pretty large number, 631 meters per second squared. And remember, this acceleration is always pointing toward the center of the circle. So hopefully that made sense. If not, you may want to go back and watch it again. But make sure that you go back to the homework questions and use everything we just talked about to try and solve these 2 problems and have them ready for the next time you come to class.